Good afternoon, everybody. We are now moving back to larger ensemble sizes. I need to start from the beginning, I'm sorry. So now. Thanks, Alison, for the introduction. I'm talking about ensemble sensitivity and sampling error correction. And we calculated both using a 1,000-member ensemble. And before I start, I want to acknowledge some people. First of all, my supervisor, Martin Weismann, and my colleague, Stefan Geis. And then I need to say thank you to Takemasa Miyoshi and his group, who provided us access to the K-computer that we were able to run the 1,000-member ensemble simulation. And Juan Ruiz provided the boundary conditions. And for example, Jeffrey Anderson gave us assistance with his sampling error correction. My talk is outlined as follows. I will start with a short motivation, then talk about the setup of the 1,000-member ensemble simulation. We'll explain you how the sampling error correction works and how we evaluate it. And at the end, I will address also the potential impact of observed quantities, because we want to use the 1,000-member ensemble correlations as a proxy for the potential impact. So that's why I ended up in the session. And then I will conclude. So motivation, why do we need the 1,000-member ensemble simulation? So we want to calculate correlations and sensitivities. And if we have a large enough ensemble, we can assume that it's free of sampling errors, so we get realistic correlations using this 1,000-member ensemble simulation. And here on the right-hand side, you can see one correlation field calculated with the 1,000-member ensemble. And what you see exactly is, so we use the precipitation inside of this small box and correlated it with the initial conditions, in this case, 350 hectopascal humidity. And then you can see, yeah, the correlation pattern looks nice. So we have these correlations now, and we want to do two different stuffs, as I mentioned in the beginning. First of all, we want to use the correlations to estimate the potential impact, which can be used to develop observing system strategies. If you think of the large data amount that is available already now, and it will be increased even more in future, so we need to find ways to choose which observations we should assimilate first, and because we have limited resources, and yeah, that's the main goal of this project, and we want to use the correlations, and because it's way cheaper than running multiple OSDIs, for example. And so the second goal of the study was to use this 1,000-member ensemble, do subsampling to see how sampling errors look. So here, this is an example of a 40-member ensemble, and so the same correlation field as in the beginning, and you can see we get lots of spurious correlations all over the domain. How's the ensemble setup? So first of all, we initiated the 1,000-member ensemble from a GFS analysis, so NCEP analysis. And we had a spin-up of 1 week, and then we get each new boundary conditions every 6 hours. We use the GSF 20-member global ensemble, and the domain is centered over Europe, so center over Germany. And we have a large domain which has a grid spacing of 15 kilometers, so that's the cycling domain. And we're doing a 3-hourly cycling over here. And then, after we have done the cycling, we do a downscaling to 3 kilometers to get to convective scales. And we use a 15-kilometer grid spacing forecast, which is run on the large domain to drive our convective scale simulation. So how do we calculate our correlations? We use ensemble sensitivity analysis. So we're looking at the linear relation of a forecast response function J to an initial quantity or state variable x, and this can be described by the sample correlation and the standard deviation of J and x. And then if we only want to have a look to correlation, so we take the correlation only over here. And so if you think of this correlation, we can get values from -1 to 1 because it's normalized. So that's the red line here in this graph. So now the sampling error correction comes into play. If we apply the sampling error correction, this is a statistical approach. I'm not going into detail, but you have to know that there are some assumptions that go into the sampling error correction. So it's calculated using an offline Monte Carlo technique. And this provides a lookup table for a certain ensemble size and correlation value that you get. And what is also really important is the assumed prior distribution that you take to calculate the correlation. So in this case, it's a normal distribution that was assumed. And what the sampling error correction does, it's systematically or statistically corrects for sampling errors. So if you have a smaller correlation value, you more likely have a larger sampling error, so you need to correct more. And if you look at the solid line here, so this is, for example, how the correction looks for the member ensemble. To go on, so I will show now a simple example of a temporal correlation. So in this time, we are looking at a correlation of a 3-hour forecast, so precipitation after 3 hours of forecast to the initial 2-meter temperature field. So you can here see again the precipitation event on one of our forecasts, and then again we are using this metric here, so the precipitation average over this box. And in red, you can see also the streamlines of wind, so you can see that there was a south to northward wind at 500 hectopascal. And then how's the correlation field? So we can see a negative correlation south of the response function, which makes sense if you assume that at earlier lead times we can have a stronger precipitation, which leads to a cooling at the surface. So colder temperatures in some of the members indicated a stronger precipitation at a later forecast time. So that's the correlation what we can see here now. If we now look at different ensemble sizes, you can see again here the 1,000-member ensemble sensitivity field. And then if we reduce the ensemble size by a factor of 5, there are some spurious correlations popping up. And if we again reduce this of another factor of 5, we see that there are various spurious correlations all over the domain. So what happens now if you apply the sampling error correction? We can see that it is able to correct for sampling errors, and it does not remove all sampling errors, but it's a clear improvement. And in the following, I will always compare the sampling error correction to an approach which was first used by Thorne in 2010, which is just a simple confidence test checking if the correlation is significant. And you can see what this does. So it throws away more correlations, and it only leaves the strong correlations that are significant. But I have to say that this is not appropriate for data assimilation because we have no homogeneous field afterwards. So this is only good for qualitative analysis as it is done for some sensitivity sometimes. So how is it if we now look at larger statistics, not only one example? So what you can see here is the frequency distribution as a function of the correlation value. Again, for the example pair that we showed before, precipitation correlated to 2-meter temperature. And you can see that the probability density function is shifted towards negative values, which agrees with the negative correlation we saw before. And then you can see if we, like the solid gray line, the bold one is the 1,000-member ensemble distribution, which is not as, which has a smaller width than the 40-member correlation distribution, which is Gaussian shaped. And if we now apply the sampling error correction to the 40-member ensemble, you can see that we clearly improve the distribution, which is very nice. And if we now want to know, okay, where does the sampling error correction has its largest effect, we can also plot the absolute error as a function of correlation value, and then we can see, so in black you can see what is the error of the 40-member ensemble compared to 1,000 members, that the major improvements are visible for small correlation values. And we can also see in this case that there are some degradations for large correlation values, but this is likely an effect due to our small sample size, which you can see here. So we have a very small number of values for a larger than 0.3 positive correlations. And it might be also due to the very general prior assumption that went into the sampling error correction initially, so we could improve this easily. To go on, I will now show you how the sampling error correction performs as a function of ensemble size. So you can see here for 48 and 200 members, the sampling error that we make compared to 1,000 members. So we can see increasing the ensemble size reduces the sampling error. And again, if we apply the sampling error correction for all the ensemble sizes, we see a clear improvement. And if we now also look at the magnitude bias, so only the magnitude of the correlation value, we can see that the improvements are even larger, which is also nice. And which was very surprising for me in this case was that using the 40-member ensemble plus the sampling error correction even performed better than an 80-member ensemble. So this was really a nice result. Going on, we not only want to look at one pair of correlations, we evaluated several different variables, and we can see that the results are consistent for all different combinations of spatial temporal correlations with precipitation. Again, for both RMSE and bias, we see a clear improvement applying the sampling error correction, which is really nice. And yeah, so I will now move on to spatial correlations. I think this is the interesting part for the data transmission people here in the room, because this is really important if we think of the background error covariance matrix. And in this time, we don't look at correlations with precipitation. We look on the left side at a correlation of 2-meter temperature with 2-meter temperature. And you can see here on the left side the mean absolute correlation as a function of distance, and here the mean absolute error as a function of distance. And we can see again, also for the spatial correlation, we see a clear improvement and reduction of sampling errors applying the sampling error correction. But we also can see a slight degradation, which is also related to this prior assumption. And Jeffrey Anderson, who suggested this sampling error correction in 2012, already thought about that problem and adapted it in his 2016 paper. So this paper is about how you can improve the prior assumption to improve the sampling error correction. So it's now a climatological prior which clearly performs better. And I would assume, so we could not test it here in this case, but I would assume that this behavior will then change. And then if we look at the cross correlation of, for example, 500 hectopascal temperature with humidity, you can see it doesn't matter which distance we look at, we always see an improvement applying the sampling error correction. And now I want to come to the part where we want to show that we can use the accumulated square correlations as a proxy for the potential impact of observations. And so up here you can see our definition of the accumulated square correlation. So we sum up all correlation values over our matrix and also over our state variables. And then you can see plotted here the accumulated square correlation as a function of ensemble size. Initially, you can again see the overestimation of the absolute correlation due to spurious correlation. So if you increase the ensemble size, we see a saturation, which is really nice. So that means that our 1,000-member ensemble is large enough to estimate the potential impact. And this is the case for all variables that we checked and that we looked at. And if we go now on and look at the what happens if you apply the sampling error correction in this case, you can see, I will switch back and forward, that if we apply the sampling error correction, we see a reduction of the sampling error again, and which was really nice that for 200 members, including the sampling error correction, which is now here the black solid line, we get really close to what we got using the full 1,000-member ensemble. And this was the case for all variables again. So this means that our 1,000-member ensemble is large enough to estimate the potential impact, but we also can gain valuable information with smaller ensemble sizes, combining them with the sampling error correction. In both cases, here the t-test also performed quite okay. And again, a proof that we're quite good with 1,000-member ensemble is this dot here at the end. So this is a 1,000-member ensemble combined with the confidence test, which is a proof of the confidence. So we see nearly no change applying the confidence test to our correlations obtained for the 1,000-member ensemble. So to conclude, so I showed you the first convective-scale 1,000-member ensemble simulation over Germany. And we evaluated spatial as well as spatial temporal correlations and showed that statistical sampling error correction can significantly reduce sampling errors. There is potential for improvement if we adapt the assumptions that go into the sampling error correction. If we think of a data dissemination application, the sampling error correction is especially helpful, I would say, for convective-scale applications or localization in the vertical, because there the Gaspari comb function won't perform that good. And if you think of a comparison between the confidence test with the sampling error correction, so a confidence test is suitable for qualitatively analysis, as it is often done using ensemble sensitivity analysis. But if you think of a data assimilation point of view, we need to use the sampling error correction to correct for sampling errors or to address sampling errors. And the accumulated square correlations can be used as a proxy for the potential impact. So thank you very much.
Okay, thank you, Tobias.